Hi, welcome to Gravity Pulls Pixel, a program that simulates gravity pulling on a white pixel on a Circuit Playground Express from Adafruit. Let's look at a little video of how that works, and then I'll come back to show you how the code works. Here you see we're using the Circuit Playground Express library from Adafruit to simplify the programming. Here I define that the distance between the neopixels around the CPX is 30 degrees. And here I've defined standard gravity. The blue pixels are this shade of blue. This is used for kind of anti-aliasing. And this defines a length of an arc in which the pixels are white. This arc surrounds the down point. Let's go to the main part of the code. Here we're setting all the pixels to very dim. And here we're computing the pixel angles. Let's look at how this works. They're 10 pixels, but they're arranged kind of like the 12 hours of a clock. And if you consider pixel 0 and put that at the bottom and pixel 5 at the top, then the accelerometer will report that that's 300 degrees. Then if you rotate that clockwise a 1/12 of a turn, 30 degrees, so that pixel 1 is at the bottom, then that angle is 330 degrees. And the way this works is a list comprehension. We're going from 0 to 11, skipping 5 and 11, and starting at 300. Remember I said pixel 0 is at 300. And then adding pixel spacing angle, which is 30 times n. So this gives us the numbers 300, 330, and because we're doing a modulo operation with a modulus of 360, once we reach 360, it starts again at 0. So 300, 330, 0, 30, and so on, skipping the 5 position. Okay, back to where we called that from here. Now look at the main loop. If you set the switch to the left, you're turning on debugging, which logs some interesting information to the serial port. Here we pull the x and y parts of the acceleration from the accelerometer. And here we compute the down angle based on those x and y values. And let's look at how that works. Here's a function called angle in degrees. And it uses the inverse tangent function to give you the angle in radians from minus pi to plus pi, which we then convert to degrees. Then those units aren't really convenient, so I want to turn them into 0 through 360, so that's what we do in this function. Then we set a magnitude limit to standard gravity, and we use that. We calculate the magnitude of the acceleration using the Pythagorean theorem and x and y. We limit that to the magnitude limit, and then we divide by the magnitude limit. And the result is a normalized magnitude that goes between 0 and 1, where 0 is there's no pull from gravity, and 1 is the maximum that we care about, which is standard gravity. Pixels lid is used for the debugging information. Here's a loop where we consider each pixel and set the value for the pixel here. And we have to find the pixel brightness if it's white. Otherwise, if it's a background pixel, then we use the background color. Let's look at what we have to do to find the intensity or if it's a background color. We need to call pixel brightness, which needs a couple of things: the degrees between the pixel position and the down angle, and then the magnitude, because we scale the brightness based on the tilt. If you hold it like this, where gravity is pulling all the way down on the white pixel, it gets bright. Let's look at the degrees between the pixel position and the down angle. We'll go to this function. And if you imagine you have a circle and you want to find the distance from here to here, the shortest one, you go this way, you don't go this way. So that's what this is doing. And now that we have the degrees between, we can compute the pixel brightness, and that's done in this function. I have to fix this comment because it's wrong. We have to consider half that lighting arc length. We're going to use it in a moment. First, if the acceleration is not enough, then we're not going to light this pixel white. We're going to return none, and this will be a background pixel. If the magnitude is enough, then we look at the distance from down, and if that falls within the lighting arc, then we continue. So continuing, we want to know how near the pixel we're considering is to the bottom point, and we compute this normalized nearness, which is a number between 0 and 1, meaning it's as close as it can be, or it's as far away as it can be while still being going to be illuminated. And then we compute a scale factor from the maximum intensity, considering the minimum brightness and the magnitude. And then we compute the color part by starting with the minimum brightness, and then we add in the normalized nearness, the number between 0 and 1 that indicates how close we are, that times the scale factor. And that's going to give us a number between min brightness and 255. Going back, now that we have this PE, this brightness value for the pixel, we use it to set the pixel. If it is not a background color, then we have equal amounts of PE in red, green, and blue. If we got none back from pixel brightness, then we're going to use the background color. And if we did make a white pixel, then we add that to the pixels lit here so that it can appear in the log. And then here's code to present some interesting information in the log. Okay, so hope you enjoy Gravity Pulls Pixel. See you next time.